morning, and hello everybody joining us today for what is our fifth delivery of the Cost-Effective Code Compliance Series 2018 Energy Code. We'll be talking both about Seattle as well as the Washington Energy Codes, and today we are going to be focusing on water heating. We have a couple of presenters today. You're going to get to meet them in a little bit. Can we go to the next slide, please?
Let's try.
Let's try. Awesome. So before we begin, you'll notice that everybody is muted. This is our fourth delivery this year, so hopefully you're used to the treatment. However, you can use the chat function on your dashboard to engage with us, ask us questions, give us comments. So please engage with us. Any questions you may have, we'll be either answering in live or answering them in the chat themselves. There's going to be some polls at the latter end of the presentation, just so we can get more information from you, the industry, of how you are going to be approaching code compliance, and that's going to be great for City Light when we're going to be doing a little bit of our program in incentive development. After the webinar, there's going to be like a 30-second survey. Please take it to let us know how we've done. Also, a recording of this presentation, as well as a handout of the PDF of the slides, will be available on our LDL webpage. That is www.lightingdesignlab.com. And if you have any questions, you can email us at lightingdesignlab@seattle.gov. Next slide, please. I just wanted to make a little bit of awareness. My name, again, I didn't introduce myself, Armando Berdiel, Technical Development Supervisor at Lighting Design Lab. We're going to be here with Duane Jonlin from the Seattle Department of Construction and Inspections. And at the latter end of the presentation, you'll get a chance to speak with Julie Banerjee from our Customer Care and Energy Solutions Division. She's one of our program implementers, and we'll be getting some feedback from you and some great discussions. All of us, part of Seattle City Light in the city of Seattle, but we also have a presenter. So let's meet our presenters officially. Duane, take it away.
Well, thank you. For those of you who might have missed it earlier, Energy Code's just one of that whole shelf full of codes that you'll have to comply with. So we're in the process of switching over from what we call the 2015 codes to what we call the 2018 codes. And yesterday afternoon, the mayor just signed the code legislation, so we're off and running. 2018 IECC was published just prior to, you guessed it, 2018, and thus the name. During 2019, we hashed out the Washington State amendments, and last year, in 2020, we developed the Seattle amendments, and then we delayed everything a few times due to the COVID crisis. But here we are, finally in 2021, implementing the 2018 Energy Code, as we call it. And at the national level, if you can believe it, they're already launching into development of 2024 codes. So outside of Seattle, the new code went into effect already last week. Just yesterday, the mayor signed the new Seattle code, and that'll go into effect for any permits applied for starting March 15th in Seattle. So of course, we're expecting a huge rush to the permit counter during this next 5 weeks as everybody tries to get in under the wire. And I've shown some variation of this slide for just about every talk I've given this past year. What we're saying is that climate change is not just some abstract idea they're arguing about in European conferences. It's a serious, rapidly looming threat, and both Seattle and Washington State are taking urgent actions to deal with it, which is providing leadership actually for other states and cities around the country and beyond. And we've set these goals. Now our task is not to argue about whether the goals are the right ones, but to find the most sensible and economical path to reach there. So of those 4 guiding principles you've seen, water heating is central to both decarbonization and efficiency. For many apartment buildings, it's the biggest single load category. Now that our envelopes are getting so much better, space heating is starting to shrink back as a big deal. You'll note that I didn't include on-site renewables here, even though there are perfectly good solar water heating systems out there. My prejudice is that solar photovoltaics have no moving parts, nothing to leak. Electricity can easily be exported to other uses when you have excess. And so I'm I'm leaving that out of today's water heating thing. But we have a special guest today, Colin Grist. Can you tell him who you are, Colin?
Yeah, thank you, Duane. Good morning, everyone. My name is Colin Grist. I'm a mechanical engineer with Ecotope, an engineering firm here in beautiful sunny Seattle right now. And like Duane said, we're looking to achieve energy savings to align both with state, local, and global goals. And for your building, it might make most sense to implement heat pump water heating or a heat pump water heating system to achieve that energy savings. So on the left-hand side of the screen there's the baseline multifamily building and a pie chart of it. The orange and the red are the temperature maintenance and the primary heating load. Both of that is the domestic hot water system. So you can see about 25% of the energy that we put into a building over the course of a year goes into heating water and keeping that water warm for the occupants. If we apply a heat pump, and that's that kind of white VRF looking device in the middle, the heat pump water heater to that domestic hot water load, we can reduce those loads by 2/3 so that we can save an enormous amount of energy. And this is just addressing one system, which is often in the basement or a parking garage or on the roof of your building, whereas other efficiency measures, although they do achieve great energy savings like heat pump water heating, you might have to alter all aspects of your building to get those. And so today we're focused on that domestic hot water room and how to make it a more efficient and sustainable system.
All right, so launching into the code itself, you might have noticed if you looked at C404 ever that there's this big hairy looking table of equipment efficiencies with these crazy looking equations like I put there on that second bullet. But I'm pretty sure that these just reflect the federal standards that all the equipment out there has to meet anyway. So somebody please tell me if I'm wrong here. The only situation I can think of where this would matter is if someone were trying to reuse another heat pump or from another project and bring it over that might have been an older unit. There are some rules for efficiency of large boilers, and in fact, there's one set for hotel and multifamily and another set of rules for all other buildings. And you have to pick one of these options from a list. So I've shown the options side by side on this chart. The hotel and multifamily column accepts equipment that's 5% better than that standard, whoopee, while the all other column has a weird list of exceptions, including one for equipment at grade level. Colin, why does that matter? And another for buildings taller than 4 stories. So if your project's outside of Seattle, you'll have to figure this out. Inside Seattle, these are only applicable to hotel and multifamily till the end of this year, at which time we're going to go over to heat pumps anyway. I should mention that at least one city council member has announced an intention to apply this rule to all the other commercial building types. I was able to talk him out of like putting it into the legislation right now because that would have delayed us even more months to get the code in. So I expect to see some legislative action on that in the next couple of months, and it might be that this is not just a hotel and multifamily thing, but something that applies to all the commercial buildings with large heating, water heating loads. So this one slide is the main reason for this whole seminar, and why we invited Colin, because he's like one of the top experts in the region, and it's something that hasn't been tried code-wise anywhere else that we know of. It says no electric resistance or fossil fuel water heating, and then if that weren't clear enough, it says you got to use an air source heat pump of some kind, and we'll see that there are several. So we put in an exception that allows solar thermal or wastewater heat recovery or ground source heat pump, et cetera, to offset heat pump capacity. So if you want to go there, hey, knock yourself out. We also put in an exception for using the NEA advanced heat pump water heater specs for central service systems. which is a standard that doesn't even exist yet. I was on a conference call just yesterday. They're sort of figuring out what that is, but who knows, maybe later this year they'll pull this together. It'll be a standard that will look at the whole system instead of just a piece of equipment, and have an efficiency rating for that entire system. But now we'll turn it over to somebody who actually knows how heat pumps work. That would be Mr. Colin there.
So thanks, Duane. I like to think that I know how heat pumps work, at least most of the time. I've been working with heat pump water heaters at Ecotope for the past 7 years, both in the building and in the design phase, and working with manufacturers to determine what works best for their product in a given application. And so I'm here to talk to you and to share some of that knowledge today. And the first thing that I want to cover is the 4 components that make a functional central heat pump water heating system. So the next slide is these 4 components. And I'll have a slide or a group of slides on each one of these, but going over this, on the left-hand side of the screen, we have our primary heaters, and these are air source heat pumps in most situations. And there can be a backup source there. Number 2 is the primary storage. This is where we're storing water. Often heat pumps are split systems where the common gas boiler has everything packaged into one unit. And then there's a temperature maintenance system, which we'll get into more details later on. This is often the system that causes a lot of headaches for early designers and implementers of heat pump water heating systems. And then the last thing we have is the mixing valve, and we'll get into that a little bit later, but that's providing tempered water out to the building fixtures and occupants. So moving on, Duane. So the heat pump water heater, this is the engine. It's not a boiler. It is moving heat from one source to another instead of making heat. And so here I show a variety of heat pump water heater units. They come in all shapes and sizes. There are some that are large, like the one on the bottom left-hand side of the screen and the middle 2. And then other ones are smaller, usually less than 5 tons. And these can be integrated package units shown on the upper right-hand side of the screen, or the stand-in unit that's middle low. Next slide, please. Not a boiler. It's moving heat instead of making heat. And so let's talk briefly about heat pumps and how they work. And I know we probably have other than engineers like myself in the audience, so I've tried to simplify this as much as possible. But essentially on the left-hand side of the screen, we have a heat pump connected to a storage tank. And it is an air source heat pump, so it is operating to extract heat from air, and that's the green evaporator portion. This is the free heat, or the heat we're doing very little work to get. And we're capturing this heat, and after we capture it, we compress it. And this is where we're putting work in, or the orange area on the screen and on the graph to the right. And so here we're lifting the pressure and temperature so that during the next step at the condenser, the red zone, we can dump all that heat into the water. And so here it's pretty visually easy to see that we get 2 units of free energy in, we put 1 unit of energy into the system, and we get 3 units out in useful domestic hot water, not electricity like we put into it. And then there's an expansion valve that essentially brings us back to the original state. And so this cycle operates to move heat from your air source and put it into water. A water source heat pump and a geo source heat pump work in the same way, but instead of air, you have a different source. Your refrigerator in your house, if you have an air conditioning system, your VRF mini split, those are all heat pumps, and they're all operating in the same cycle. They're moving heat from one source to the other. So this is not a new technology. It's been around for a long time, It just might be new to you in this application. So next slide here, Duane.
Before you go on, Colin, can you just explain in your lower left diagram, which part of that orange circuit is the refrigerant liquid and which part is it gas?
So the evaporator and the compressor will boil the refrigerant, and so then it's essentially in a gaseous state after the compressor. And then as it goes through the condenser and the expansion valve, then it goes back into a liquid state. However, that's not the case for all heat pumps, and that's a pretty technical detail involving the transcritical cycle and that triple point on top of the graph that I won't get into.
Okay, thank you.
Level 2. And we can skip forward. So there's two primary types of heating cycles that heat pumps operate in, and these are really critical to understand. There's single pass, where it's taking cold water in and it's heating that water to the discharge water temperature, commonly around 140, sometimes 135, 145. And so that's one pass and it heats the water all the way up. Multi-pass is what it sounds like. It takes multiple passes to heat the water up to temperature. And it's often doing a 10-degree lift on the water instead of a much higher 70 to 90-degree lift as a single pass device will do. And it's critical to understand these and apply them in the appropriate way. And we'll get into that shortly with discussion on the temperature maintenance heating systems. And so the second component, we finished talking about the heat pump or the engine. We're now moving on to the battery bank or the hot water storage tanks. Heat pumps, their capacity is more expensive than a gas water heater. So we often provide more storage and less heat capacity to meet a given load than you would in a gas water heating system or an electric resistance heating system. And so here on the right-hand side of the screen, there's 5 storage tanks in series. And this was done to get a larger equivalent storage volume. And you can essentially think of these storage tanks stacked one on top of the other in a vertical arrangement. And so we have hot water at the end of the storage tank and cool water at the beginning of the storage tank in number 1. And so here, the important thing to understand is that heat pumps make hot water, but they need a place to store it in your building. And it might be advantageous to upsize that storage when compared to a gas or electric resistance system due to the cost of heat pump capacity. You can also configure your tanks in parallel, although if you have more than 2 or 3 tanks, you do want to get equal balancing through those tanks. And that can be achieved in a few different ways. But when you're putting lots and lots of tanks together, like 5 shown here, doing parallel tanks becomes challenging to get balancing through all of the parallel systems. So moving on to the next area of discussion, which is tank insulation.
Well, I'll just mention, here's a code requirement that is unique to Seattle. If you have one of these storage tanks, it's not, the heat pump itself, it's a separate, just plain storage tank, and you're going to hold the water at more than 130 degrees, and I'm sure Colin will tell you some reasons to do that. We're just saying you've got to wrap that thing in at least R2 extra insulation for every 10 degrees increase. And so if you want to store your water at 170, that'd be 40 degrees higher. So that'd be an extra R8. Really, the insulation typically comes in R11 thicknesses, and there's some specialty products that just, I think, Velcro around your tank.
So the next part of the system is the temperature maintenance system. And this is keeping the water hot in the distribution piping. With central heat pump water heating systems, we often have extended piping lengths before the end use fixture. And so we're continuously circulating water when there's occupants in the building to keep that water warm near the fixture, so they don't have to, or so that the user doesn't end up opening the tap, drawing a bunch of cool water out until hot water arrives at the fixture. The temperature maintenance system is often the system that most designers have issues with when specifying and installing heat pump water heating systems. And this primarily comes down to heat pump water heaters operate most efficiently and reliably when they take cold water and make it hot. Their heat exchanger, their compressor, it's sized to do that task. They're often constant speed or constant heat capacity devices. They operate at a given point, and they don't vary capacity like other VRF systems or systems do to match the load. And so with the temperature maintenance system, you're often circulating warm water back to your storage volume. And if that water is taken back to the primary storage volume, the single pass heat pump water heater that's serving that may have issues heating that water depending on what technology is used. So that's why there's multi-pass heat, or that's where multi-pass heat pumps make more sense. They're designed to do that 10-degree lift and better suited to reheat those hot water circulation loads.
We do have a question on the storage. What is the baseline R value for the storage tanks in Seattle? Question from Bob Baird. He believes ASHRAE recommended that the value was R13. But what is that baseline R value for Seattle?
I think that there's already a standard for that, isn't there, Colin, for the insulation that's integral to the tank before you add any extra?
I don't know what it is off the top of my head, but I think R11 is standard. R16 is a common tank insulation rating too. But we can get back to you on that question.
Thank you. Thank you.
And the mixing valve. So with heat pump water heating systems, you can store water hotter than you're delivering it to the occupants at 120 degrees. It might be advantageous to store it at 135 or 145 for safety concerns, or to get more effective storage volume in your storage tank because the water is overheated. So this device is mixing down the water so it consistently goes out to the fixtures at 120 or somewhere about there, so we don't scald occupants in the building. And on the top right-hand side of the screen, we show a very large dual thermostatic mixing valve with parallel circuits. And this is done to get good control over both the high and low flow rates in a building that are typically seen. But you don't have to have a massive thermostatic mixing valve like that one on the top side of the screen. Electronic mixers also come in much smaller sizes, all the way down to 3/4 inch, actually potentially 1/2 inch for some manufacturers. And below on the bottom right, there is a 1.5 inch valve that's serving a 60-unit apartment. Electronic mixers are critical to heat pumps because the storage temperature is often fluctuating a little bit more than in a gas water heating system. And that fluctuation needs to be responded to in the mixing valve. Certain paraffin wax types of mechanical valves are just slower to respond, and that can be concerning with these systems. Electronic mixing valves often or typically operate with solenoid valves and can be much quicker to respond and operate in a much tighter controlled deadband. So those were the 4 components that all together comprise a functional heat pump water heating system. Next slide, Duane.
Let me just tag on to that last slide about the mixing valve. Just if your system just has one single riser or one single zone, the pump will turn off when the water temperature in the loop hits a certain level, and then turn back on after it drops 10 degrees. You can set what that target level is. And you could also have, and this is just to keep the pump from just running continuously if you had a 3-day weekend and nobody in the building. You could also have a time switch function to turn it off completely during off hours. If you've got more than one riser or zone, you need controls that can turn off the pumps when there's a long period with no demand. And in Seattle, you need a self-actuating thermostatic balancing valve. Now, if that wasn't exciting enough, your electronic TMV has to be the type that will either go fully to cold or maintain its current valve position during a power loss or a water flow failure for some reason. Just a couple interesting things to know. Now, back to Colin.
Great, thanks, Duane. So those are the 4 components that make our functional heat pump water heating system. We have an engine, something to move heat into our hot water. We have a storage tank, a place to store that water that's heated. And we have a temperature maintenance system to address the large circulation systems in the building. And then a mixing valve to control our water temperature going out to the occupants. Now, because 4 isn't my favorite number, I also have 4 key design considerations for functional heat pump water heating systems, and we'll go through these together next. The first one I've highlighted is the building hot water distribution system, and the biggest thing here is its impact on thermal stratification and how heat pumps can deal with that. So here we have a pretty typical 5/2 multifamily building floor plan, and we show a plumbing distribution system with risers coming up through the units, and then they're connecting to a hot water recirculation line in the corridor that then is routing back to the basement where the heat plant is. And so that little box on the left-hand side of the screen essentially shows this conceptually, where we're pushing hot water out in the red line. It's going up in risers, serving a handful of apartments, and then being collected at the top and returned back to the central plant. Because we're returning warm water back to the central plant, we're going to impact the thermal stratification. And this is really important to understand how single pass heat pumps deal with this and how multi-pass heat pumps deal with this. So Duane. So
this is me, an architect, getting out onto really thin ice, but Colin here will let you know if I screw up. But we got, as he's mentioned already, you've got 2 basic flavors of equipment, single pass and multi-pass. Single pass just bumps the incoming cold water up from 45 degrees or whatever to maybe 130 degrees in one fell swoop. It's really not happy if it gets fed water that's too warm. So that one requires the recirc water to get its temperature boost in a completely separate system. That's the code language here. Multi-pass systems, on the other hand, boost the water up to the required temperature in several stages, so it's not such a big problem to let those reheat the circulating water. Before you go on, Colin, which kind are these 2 systems we've been talking about? The big garage systems and with the huge tanks, or those sand and CO2 systems, are they typically single or multi-pass?
Single pass is better suited to serve the primary heating load. And then the multi-pass is sometimes present to serve the temperature maintenance heating load, but we can also use an electric resistance water heater in a swing tank configuration, which we'll discuss shortly. But going back to why is this in the code? Why do we care? Well, it can make or break the system. And so it's it's either going to work or not going to work, and this component has a significant impact on that. And so why does it matter? Well, it impacts thermal stratification. What is thermal stratification? It's essentially having cool water at the bottom of your tank, a very thin transitional layer, and hot water at the top of your tank. A mixed tank is what's shown on the right-hand side of the picture here, where we have a little bit of hot at the top and maybe a little bit of cold at the bottom, but primarily the tank is orange colored or around maybe 110 degrees. And so thermal stratification does impact both your effective storage volume, because now you have essentially lukewarm water in most of your tank versus hot water in your tank. And it also affects the heat pump cycle. And so on the bottom left-hand side of the screen, we have our pressure enthalpy diagram again for all the engineers, and some colors for all the non-engineers. And when we get free heat out of the system, we compress it, and then we're dumping it back into the water. If we dump it into warm water, we drop down on that purple line. And so we're cutting our cycle short, we're reducing our efficiency, we're reducing our heat capacity into the system, and we might be starting to have a control issue that will come. And so it's really important to, with single pass heat pumps, use the full heating cycle and dump water back into, or have cool water to dump heat into rather than warm water. And moving on to the next slide, I'm going to cover this a little bit further. So with single pass primary heat pump systems, it requires a dedicated temperature maintenance system, as the code section says. So on the left-hand side of the screen, we have that single pass primary heater connected to a single storage tank with a temperature maintenance heater connected to a temperature maintenance storage tank. That temperature maintenance heat pump is configured in a multi-pass arrangement so that it's designed to heat up the water 10 degrees and not designed to heat up the water 70 to 90 degrees, like the single pass equipment on the far right side of the screen. This results in better equipment reliability because it better matches the load with the heater and the heating cycle that it's operating in. It also reduces the amount of storage volume you need because it increases your effective storage volume. You can also store water in that primary storage tank above 120 degrees at 135 or 145, and that's going to further increase your effective storage volume because we're delivering water to the occupants at 120 degrees. The single pass system also results in a higher heat pump water heater COP, or coefficient of performance. So it's a much more efficient system. And so it's both the heat pump COP and the full system COP. And with this type of system, you do get some redundancy in the system design, as you have two heating sources. We'll talk a little bit more about that later. On the right-hand side of the screen, we have the multi-pass heat pump, and this is more of all eggs in one basket scenario. Here, we're returning hot water circulation back to the storage tank, and this one device is heating both the primary domestic hot water load, what the occupants are using in the building, and the temperature maintenance load, keeping the water hot in the pipes. What we see here is because there's a difference in the scale of the load, the temperature maintenance load is small and very constant throughout the day, where your primary heating load is much bigger and periodic throughout the day, that if you provide one air source heat pump to meet both those loads, due to the scale of those loads, and because heat pumps are most often constant heat capacity devices, you might run into cycling issues as the unit tries to cycle on and off frequently to meet the temperature maintenance load, and then do one bigger cycle to meet the primary heating load. There's also sizing concerns, as the hot water loads are different, and so putting staging or providing multiple multi-pass heat pumps in a parallel arrangement, and then only turning on one or two or all of them to meet your bigger load is a great way to address that concern. And then the main thing is with multi-pass equipment, you often have to have a lot more storage volume because the effective storage, or you have a much lower effective storage efficiency, storage efficiency in your tank. And then because multi-pass heat pump water heaters aren't operating that full heating cycle, extending those bounds, they often operate at a lower COP or coefficient of performance. And then
if you don't, sorry to interrupt, Colin, if you don't mind, for just a couple of questions on we have a question called why can't the single pass system be used for residential radiant heating systems?
That's a great question. It can, but very with lots of limitations. And why is because most residential heating systems, a fan coil is designed for a 10-degree drop across it. And so that's operating like your temperature maintenance system. You're essentially sending out water at 120 and it's coming back at 110. And so a single pass likes to take cold water and make it hot, and a multi-pass can take warm-ish water and make it hot. And so that's why a single pass doesn't work well in an HVAC application with water as the distribution for the fluid.
We have one more question for right now. Excuse me. And it says, is there a minimum number of apartments approximately that would be cost effective for a primary and temporary maintenance system?
What we've seen is that when you have small apartments, you have small distribution systems. And you can often design the piping so that you don't really need a recirculation system. When you start to grow the apartment size, the hot water load also grows and the distribution system grows. And so that's when you need to have a dedicated temperature maintenance system. I don't have an exact number on what point that is, but I would say 10 apartments or less. If you get really clever, you could have a very small distribution system or a very efficient one, super insulating it to minimize the requirement for a temperature maintenance heater.
Thank you, Colin.
All right, Duane, I think we can go on to the next one. So 2 options for temperature maintenance. Let's say you do have a single pass heat pump water heater and a big distribution loop in your building. So what are my options? On the left-hand side of the screen, we have the parallel system, where you have a single pass heat pump water heater connected to a primary storage tank, and that is in parallel with the temperature maintenance tank connected to a multi-pass temperature maintenance heater. And so here they're each serving the load and their size to meet that given load. Another way to deal with the temperature maintenance load and still reheat it with the heat pump is with use of the series or swing tank concept. So here we have our same single pass primary heaters on the left-hand side of that image, serving a single storage tank, but we're putting 150-degree water into that primary storage tank. That 150-degree water is flowing out of the top of the storage tank and into the bottom of the temperature maintenance tank, which in this scenario is just simply an electric resistance storage tank. So anytime 150-degree water flows out of our primary storage into that temperature maintenance tank, it's also mixing with 110-degree water coming from your hot water circulation system. And so what happens is that small amount of draw of overheated water is enough energy to offset the losses in the temperature maintenance system. And so this is a way to essentially use your primary heaters to reheat the temperature maintenance load really efficiently.
So Colin, in this case, the electric resistance heating element in the lower right doesn't run that much, right?
Correct. So the intent here is that the overheated water and the regularity of it throughout the day is enough to move energy from our primary storage into that temperature maintenance. And therefore, that electric resistance coil, if the set point is correct at, let's say, 125-ish, then that coil won't operate because we're essentially reheating the hot water loss or hot water circulation losses with our primary heater. And that temperature maintenance swing tank is sized specifically because you're essentially using the volume to act as a buffer. So if that's a 5-gallon tank, it's not going to work very well. And so there is a sizing method that I'll cover in a little bit that helps you size that system so that it's an appropriate volume to coast through your longest periods, which are typically overnight, 4 to 6 hours in duration. And Duane, I think the next one is I think we can move on to sizing. Oh,
Right.
those are yellow highlights. So sizing.
Let me just, oh, did you want to like talk about sizing before I start talking?
No, you can go.
Okay, just here's a little code excerpt but what it says is that you've got to size your system so that it provides 100% of your calculated output requirement from, coming from the heat pump compressor when it's 40 degrees outside, and 50% when it's 24 degrees out, our design low temperature. If you're using one of those big Colmac or Rheem heat pumps down in a garage, I guess those are actually called reverse cycle chillers. Is that right? You don't have to worry about the 50% thing since it never gets down below 40 in an underground garage in Seattle. Now, so we just mentioned the reheating for the circulation water, and here's in the code it says, yes, that can be electric resistance. Also, defrost and heat trace and backup heating in case of system failure. Now, the low temperature rules are interesting. You can provide some electric resistance, supplemental heat, if it's got no bigger capacity than the compressor does at 40 degrees. And it's only used when it's below 40 out, and the compressor is sized so that it's still producing useful heat all the way down to 17. There's too much demand and finally, there's too much demand for the compressor to supply everything on its own. So you're also allowed to have supplemental heat downstream from a multi-pass system. Colin, I think we meant the recirc in that case. Is that how we wrote that part of the code? Do you remember?
So yeah, multi-pass systems, because you're getting a 10-degree lift on those systems during high draw periods where a lot of people are using water in the building, the system can, if not properly sized and properly configured, you can essentially get warmish water coming out of the top of your tank. And so it's advantageous to provide a trim heater just downstream of that tank to address any high draw periods like that might be a concern.
Okay, so it's kind of an emergency backup for a heavy load.
Precisely.
Yeah, okay. And finally, little water heaters that aren't part of the circulation loop, like if you have a janitor's closet or a lab sink or something that's a long ways from your main loop, that can also have some electric resistance. But now back to Colin to talk about real engineering.
Sizing. Heat pump water heating sizing is critical both for the system to operate well and for cost effectiveness. And so I said earlier that gas capacity is pretty cheap. Gas boilers pretty much come in 200 kBTU sizes, and so you just put a lot of capacity in and not much storage volume. Heat pump capacity is more expensive per kBTU than gas, and so it can be extremely advantageous to upsize your storage and then therefore reduce the required heat capacity to meet a given load in a multifamily building. And so on the screen here is the load profile for a typical multifamily building. There's and this is pre-COVID, and it's changed a little bit, but there's essentially a big draw in the morning as people are taking their showers, getting ready for the day. There's a lull throughout the day most days when people are at work or out and about enjoying life. And then there's more water use in the night when people are home making dinner, cleaning up dinner, and doing laundry and the other household tasks that we all enjoy doing. And so heat pump water heating systems can be sized to meet that peak design day load. And where a gas water heating system might be sized for a 3-hour recovery period, a heat pump water heating system might be sized for a 8 or 16-hour recovery period. And essentially, we're just providing enough storage volume to get through that large use period, and then we can turn the heat pumps on and let them chug for the rest of the day. This is really great, and California is jumping on this and really looking into it because it has a lot of potential for load shifting, load shedding, and to better utilize our smart grids that we're all trying to get to. Essentially turning on heat pumps when there's a lot of sunshine out and we're capturing it on our solar panels. So not only is it cost effective, but it is also future proofing your building, as Seattle doesn't have demand response pricing right now like California does, but I know lots of utilities are looking at that as a future for the United States. And so our heat pump water heating systems, we're sizing to meet that design day load. And at Ecotope, we created this pretty awesome sizer that's available online. The next slide, please, Duane. And this is the Eco Sizer. You can find it at ecosizer.ecotope.com. And it is specifically designed for multifamily central heat pump water heating systems. And right now, this is the results page that you'll get after you go through a sizing run on it. And essentially what you're doing is you are defining the number of occupants in your building, the number of apartments being served, the daily hot water usage, and some estimation of your temperature maintenance load. Then the sizing tool is outputting a graph with a slider bar that allows you to select a range of tank volumes to heat capacity to meet a given load. So the first point that is outputted here is 286 gallons and 67 kBTU per hour. So any system that has more than that will meet the load. So we just have to be above that green line. If we were to slide that blue dot all the way to the left-hand side of the screen, we'd be at 150 gallons of storage water and 90 kBTU of heat capacity. That's basically your gas water heating system there. And so if you have a lot of space in your parking garage, you can provide storage easily. You don't want to spend a lot of money on your heat capacity. You slide that all the way to the left, you're at 400 gallons, and you only need maybe 64, 63 kBTU per hour. And so this is a tool that's available to everyone with the web address there, and can be really helpful to help you explore sizing options to meet the domestic hot water load.
Colin, where does the daily hot water usage number come from?
That is user defined, and we've found that 25 gallons per person per day is a really good number for the standard market rate apartments being built throughout Seattle. But there is a slider bar for that metric that gives you a variety of options, including the ASHRAE low value, closer to 16 or 18, forget what it is, and some California nominal values of closer to 30 gallons per person per day.
Cool. And at the end of this, are we going to have a chance to look at this tool?
I would love the opportunity to do a test drive with you all if we have the time.
We won't drag along too much then.
So we've gotten results either from the EcoSizer or from a manufacturer or from a smart engineer, and it's going to say we need this many kBtu per hour and this much storage volume to meet a given load. So now we got to go select a heat pump. The manufacturer will typically publish a heat capacity rated around 70 degrees Fahrenheit, which is advantageous because it's a good rating point. It's easier to make hot water when it's warm outside, right? We all know that. However, what you need to be paying attention to is the design air condition that the heat pump will see. So if you're in Seattle, it's going to be around 23 on a day like today when it's cool and sunny and cold overnight. And so at 23 degrees, we're getting about 120 kBtu per hour, whereas at the nominal manufacturer's rating point, closer to 70 degrees Fahrenheit, we're getting around 138 or 140 kBtu per hour. The other thing you need to be aware of is defrost. Heat pump water heaters can go into defrost during normal operation because they're trying to heat water or extract heat from the air during cold climate conditions. And so the defrost rate is something that you should consider in your sizing. And you can either provide backup electric resistance like the code allows, or provide a little bit more heat capacity to meet the load during those conditions. And a defrost cycle might be at worst 25% with a very passive, we're just blowing a fan over a coil system, or it might be a lot better at 5 to 10% when we're doing a more active defrost cycle and using our refrigerant to melt ice on the coil.
But if you've got a great big storage tank next to this, then it doesn't matter if this is defrosting for 20
as long
minutes.
as you provide enough overall capacity to meet the load over your duration, which may be 8 hours or 16 hours, then you're correct that the unit can be off, or all of the units can be off, and you have a big volume of storage that is still heated, and that can be supplying hot water. 5 to 10 minutes later, when those units come back on, you still have hot water in your storage, and now you're providing heat back into that storage tank.
Colin, I do have one question when it comes to manufacturers. The question reads, when you're using a single pass and a multi-pass water heating combined system, is this typically you're using two different manufacturers or not?
It's up to the designer. I typically stick with the same manufacturer because there's then one line of support for you and others on the project.
There you go.
You always want to know that you have one person in particular to blame. If there's two manufacturers and they'll both go, no, it's that guy.
So we've sized the system. We've looked at how much heat capacity we actually need. Now we're going to talk about refrigerant and equipment selection. I'm going to try to go through this because we're 5 minutes before our break, I think. So there's options out there, but it's not the cereal aisle quite yet. There's only a handful of options, really. We have Mitsubishi has a CO2 heat pump water heater that's sold throughout Europe and Asia, and it is being ETL and UL tested now or soon. It's targeted to be available in the United States early this summer. And that's the unit kind of on the left-hand centered side of the screen. We have Nile, which is a 134A heat pump manufacturer, and that's just below that unit. Those are also big, 10 to 25 ton units. The Mitsubishi is a 10-ton unit. And that's a 134A unit, and we'll cover those in a little bit. Colmac is another 134A unit. That's to the right, the other square heat pump water heater. We have an integrated unit. These are common in residences. I have one of these in my basement, 50 or 65 gallon tank and a small compressor, and it heats water. It also dehumidifies my basement, which is an awesome measure in Seattle. So if you have a humid basement, get a residential heat pump water heater and put it in there, and all your problems will be solved. And then there's the Sandin or Sandco unit in the upper right-hand side of the screen. That's also a residential product, but it's 1.25 tons. And so we've had a lot of success gaining a bunch of those up to serve a smaller multifamily building, say anywhere from 4 units up to 60 units. And so let's talk about what heat pump makes sense where on the next slide.
And Colin, how many apartments could you get out of a 10-ton unit?
It depends on your storage, but I would say a 100-unit apartment would probably be doable. We can run that number on the EcoSizer. So here's the 3 common refrigerants that are available on the market today. We have 410A, or this is what's used in the split system heat pumps, the mini splits for HVAC space conditioning, and the VRF systems. It has a high global warming potential, around 2000, but it can work in very cool ambient air temperatures, down to about -5, and still provide hot water to the system. However, it has challenges making water above about 120. Certain manufacturers can do a bit more or a bit less, but it's, my rule of thumb is it's right about 120. Our 134A can make much warmer water. It can make water up to 160 plus. It also has a lower global warming potential, but it's not that much lower. And it does have a higher coefficient of performance, or COP, than the R410A systems. The crux of 134A is its minimum ambient air temperature, which it can't operate much lower than about 40 or 35 degrees Fahrenheit. And so that's a problem in Seattle because it gets cooler than that in our area.
And that's why we put those systems in a garage?
And so that's one of the reasons why we put those systems in the garage. And I'll have a slide on that, so I'll go into that in a little bit more detail in a minute. But we can essentially use an underground parking structure to buffer the air. I call it the poor man's geo, because it's essentially making a geo heat pump. And then R744, this is the promising refrigerant in our sunny future. It can make 190-degree water. It can operate at very cool air temperatures, and it is really efficient. A much higher system COP at about 3.2. However, there's just that Sandin or Sandco product currently available, which is the small residential 1.25 ton compressor right now, with the Mitsubishi QHV coming soon this summer. I am aware of a few other US manufacturers that are looking into and currently developing R744 heat pump water heating technologies. So it's in the future, but not here quite yet. So if you have a R134A system, Duane could skip to the next slide. It might be really advantageous to use an air buffer zone. And here I'm showing an underground parking garage, but conceptually you could use many different zones, whether they're an electric closet that has a source of transformers that are giving off heat, or some other waste or rejected heat source. So the air is coming into the parking garage at around 25, and because parking garages are typically underground and there's a lot of concrete in direct contact with that ground, they stay above 40 degrees easily throughout the entire year, even during periods where we have a week of cool air below 30. And here we can also use these air source heat pumps to provide some exhaust to the garage. As these air source heat pumps, a 10-ton unit can move about 5,000 to 8,000 CFM of air. And so that's a relatively large amount of air. And so it can be advantageous to use those to do some of the minimum garage exhaust ventilation or the continuous operation of that.
And Colin, you'd have some kind of a sensor that would switch off the main garage exhaust fan when the RCC was running?
Yeah, so in the section view, the conceptual rendering, we're showing that RCC, or heat pump water heating exhaust air, is being discharged out of the garage. And that's because we're taking it in at 40 degrees, but we're often taking 10 to 20 degrees out of it. And then we don't want to short cycle it back to those units. So we're pushing it out of the garage. On the left-hand side of the screen, with the floor plan, here we're just discharging it towards garage exhaust fans. And so when you can put an interlock between those two systems to help move some of that cool air out and reduce your short cycling potential or risk.
Thanks. So alarms, you have to have alarms on the system to tip somebody off that there's a serious problem. So you might want to get really clear about where these alarms go and who's supposed to read them. I've heard stories about fault detection alarms that went to a web page somewhere that no one in the building had ever heard of. But you just got to be able to pick up those 3 bullet points at least on your alarm system and have it go somewhere where somebody will put on their coveralls and go downstairs and see what's going on.
And that is my fourth, and one of the ones that I often like to touch on with regard to building maintenance personnel. It is extremely important that the people on the project know that there's a heat pump water heating system in the building, and they don't assume that it's your standard gas water heating system. Because we often or occasionally provide a backup system, it's really important to have a notification when that backup system engages, so that both you can guarantee the energy savings that you paid a lot of money upfront for, that you're capturing those, and you're not just running your electric resistance backup unknowingly because your occupants are still getting hot water. People complain when there's no hot water and don't complain when there is hot water, and that's really your only feedback loop in most hot water systems right now. Our cars, our cell phones, nearly everything else in our life will give us notifications, and arguably too many of them. And I believe strongly that heat pump water heaters function way more reliably, will be way less of a headache if you're attentive to them and have a way to communicate with them, have a path back and forth essentially. And that's your alarm and notification system. That system can also be used for maintenance reminders, which are extremely important, especially right after construction ends. One of the biggest issues I see is air source heat pumps in a parking garage with a lot of concrete dust all over the evaporator coil and the filter, and it just doesn't transfer heat like it's supposed to, and that's causing the hot water issue in the building. It's not a technical issue or anything, it's a routine maintenance item that just needs to be addressed. And so it's critical that you have that alarm functionality built into your system to notify personnel when there's an issue, but also to make that personnel aware of their routine maintenance procedures that need to be addressed to achieve a reliable heat pump water heating system.
Okay, well, since you've all been so good, we're actually on time for a change. So we're going to just allow you to get up and walk around the auditorium here for a few minutes. In fact, we're going to let you walk around for exactly 3 minutes, and then we'll launch back into a lot of other plumbing system and water heating system related things that are not just the heat pump water heater. So see you in 3 minutes. Well, 3 minutes goes by fast, huh? Let's launch back in here. This is one IECC code requirement that we're making less stringent here in the Seattle code. The way that this was set up, you'd have to somehow keep your public labs within 2 feet of the circulation pipe, which is bizarre. So I've allowed 8 feet here. This way you can still run your circulating pipe up above the ceiling and have drops down to your labs. The idea had been to prevent people from wasting water while they waited for hot water to come out of the faucet. But studies that have observed this show that very few people wash their hands for more than, I think, 4 seconds anyway. I actually did vote for this at a national code meeting several years ago. What was I thinking? Let's momentarily leave the energy code, though, for some recent state law. The maximum flow rates for fixtures are now equal to or lower than the water sense standards, thanks to last year's legislature. And while we're at it, notice that there are even some lower shower flow rates that are being installed in a lot of affordable housing projects I've seen, and they seem to work just fine. So since all new fixtures will henceforth be water conserving fixtures, as the plumbing code sees them, the Seattle-King County Health Department adopted Appendix M into the plumbing code here. So plumbing engineers tell me this generally lets you drop one whole pipe size, so from 2 inch down to 1.5 inches, or from 1 1/4 down to 1 inch. And this puts you into a thinner insulation category sometimes. These smaller pipes reduce your pumping volume, obviously, a lot. There's a big difference between the free area in a 2 inch versus an 1.5 inch pipe. So you can tell when you're in a really exciting seminar when the speaker has a whole slide devoted to pipe insulation, right? What could be more fascinating? So in general, you can use the table in the mechanical section, 1 inch insulation for pipe sizes up to 1.5 inches, and 1.5 inch insulation for larger pipes. But note that last exception, that the final run out from the circulation pipe to the fixtures doesn't require this. And that was put in there to accommodate pipe that gets cast into the slab in hotel and multifamily projects. Now, for the circulating system pipes, both supply and return, you have to add 1 inch to each of those insulation levels. So 2 inch insulation is required for pipe sizes up to 1.5 inches, and 2.5 inches for larger pipes. This is for the circulating system. So you would have to plan a 7 inch diameter space for every 2 inch pipe. Don't freak out quite yet. We've got good news about pipe sizes shortly. So, Colin. Colin, are you muted?
Yeah, sorry. I'm back. So pipe sizes and the distribution pipe sizes. Like Duane said, Appendix M has been adopted, and that is really great news for all of us here today. It results in much more realistic pipe sizing for your building project. So I have an example here of appendix or just sizing of the cold water main for a given building. And this is a 114 unit Seattle multifamily building. It does have the booster pump because of the low street pressure. So friction losses were not something that we were trying to minimize to the maximum, or minimize as far as possible. So Appendix M results in 260 GPM, and so that results in a 4 inch pipe. This is actually at the top range of that. size of pipe. So the designer might even put a 6-inch connection in to deal with 280 GPM, just in case an architect adds more rooms or more bathroom groups or more amenity space to the building later in the design. Appendix A and C with using the bathroom group fixtures results in 205 GPM. So definitely a reduction, but that's only bringing us down to a 3.5-inch connection, and often a 4 inches is provided in this situation. But if we size with Appendix M, we're resulting in 54 GPM for this 114 unit multifamily building, which only requires a 2-inch main. So here, there's a lot of cost savings for the installing contractor because it's a smaller pipe and it's less work to install. And there's also substantial material savings, so both material and labor savings there, as well as it reduces the amount of distribution piping and the surface area of that distribution piping in your building. And what that does is reduces the amount of hot water losses or the temperature maintenance losses as you're circulating water throughout the building. And that's really our goal with temperature maintenance systems, is to first reduce before we make up the losses. And I like to remind people of recycling at this time, where it's reduce, reuse, and then we recycle. I think most of us just skipped to the recycling portion and forgot the first 2 steps. So first, reduce the amount of temperature maintenance or distribution piping in the building to reduce the temperature maintenance load. Appendix M can be used for this, but we can also use design by doing back-to-back risers. So you have 1 riser for 2 apartments versus, and then that goes up throughout the building, hitting 2 units on each floor, versus the more standard approach to have 1 riser for each and every unit. And so on the right-hand side of the screen, we have a multifamily building with a few of each. We have on the kind of top there with the highlight is a riser going up between 2 bathrooms, and that's a back-to-back riser, and we can serve both those units off that single riser. Towards the bottom right-hand side, we have a highlighted riser off your entryway, and that's just serving that single unit there. In older buildings, we used to have a whole chase for the plumbing distribution system, and you could open that up and look in, inspect the insulation. Now all this piping is being buried in walls, and in other places that are less accessible, and minimizing the amount of locations has benefits there, not only for maintenance because it's less accessible, but also for reducing the hot water losses in the building, which will dramatically save you energy. Because I would like to remind you that the hot water circulation loss and load can be about 1/3 of the entire domestic hot water load. And that's just throwing heat out into the building year round, which is not what we want to be doing.
So Colin, I was actually wrong about being able to reduce up 1 pipe size on Appendix M. It looks like you can reduce 2 or 3 pipe sizes if you're using Appendix M.
Here we were able to reduce further. If you were dealing with building pressure only and you didn't have a booster system, this would have likely resulted in closer to a 3-inch pipe size there for Appendix M. And that's just because we're running up into a fixture or a friction loss issue at that point.
Cool. So here's, I'm taking a little detour out of water heating just to kind of clarify something. There was a lot of confusion about insulation of refrigerant piping during this past year, and a lot of arguments with the inspectors. So in Seattle, we decided to clarify it here. It's 1/2 inch insulation on the inside of the building and 1 inch on the outside of the building, and that applies to both the liquid line and the suction line. This runs counter to what's been typical practice, so you'll still hear some grumbling about it, and these all on the outside, they have to have a cover over it, but those covers do exist for that thicker insulation. So just a word to the wise there. Metering is another thing that's caused some grief for plumbing contractors in Seattle and King County, where they've replaced the whole water heating system, and in some cases even in new construction. Apparently, this requirement for metering the hot water at each apartment hadn't been enforced for ages. So new management took over at Public Health, and they started to enforce these energy code provisions that had been on the books for decades already. It's really not that big of a deal to insert little flow meters with digital outputs. Sometimes they fit in the wall cavity or under the kitchen sink or something. But if the repiping job is completely done and the finished work has all been completed, then it's a real miserable mess. So just be aware that it's a requirement that every individual dwelling unit gets a hot water meter for new construction or when you're replacing the existing plumbing system. Notice also at the bottom that water heating is one of the end use categories that has to be provided in your overall building metering system for new construction. So as you know, C406 is our system where you have to pick a few above code items from a list of a dozen or so options. Outside of Seattle, you have to get 6 credits in this system, and inside Seattle, you need 8. If you're doing a school, for instance, like I've circled there, you could pick up 4 points with the HVAC efficiency and the first lighting credit. Now, there are 2 water heating options on this list, and they're each worth a ton of points. So in Seattle, since we're making the basic version mandatory for everything next year, which is what Colin's been telling you about for the last hour, you won't be able to get any credits for that. For the high performance version, which really, the big difference is that it has low global warming potential refrigerant, we're still going to give you 5 credits in Seattle. So this would basically require one of those CO2 type units, which is cool because our cost work has indicated that the Sandin units cost half the whole installed cost of that system as compared with a traditional gas system. The increase is half as big for those CO2 units than what the big reverse cycle chiller monsters in the parking garage cost. It's what we've seen is it's $700 or $800 per unit versus $1,800 or $2,000 a unit with the costs all in. Note that some utilities might set up incentive programs based on these credits. So there's going to be a reason for getting large numbers of credits inside and outside of Seattle. Also note that the all other category over on the right side of the slide, which could apply to restaurants, hospitals, gyms, some other space types, the question mark is there because one city council member has announced that he'll propose a rule change to apply the heat pump requirement to all commercial buildings, in which case that 8 points would not be available to you for those. But we're going to find that out in the next couple months. Just to show what happens to multifamily buildings, if you do that advanced water heater option, the lighting credit is totally easy for an apartment. The balanced ventilation requirement essentially requires DOAS in apartments already, something else that's in elsewhere in the energy code. So when you add in the 5 credits for a CO2 type heat pump water heater, you are golden. Colin.
Yeah, so I want to do a CO2 heat pump water heater because I can get all the points I need. How do I make that happen? Well, Sandin is now known as SANCO 2 or SAN CO2. And they have products that are available for use. These are originally designed and marketed for the residential market, so that they're a little bit smaller than your large commercial piece of equipment. These are 1.25 tons. The larger commercial equipment is typically 5 tons or greater. However, you can put a bunch of these together to serve a greater load. And that's what we did here. We've done that multiple times throughout Seattle, typically putting anywhere between 4, 6 to 8 of these together and allowing them to stage on and off to meet a load. Small Planet Supply is distributing these heat pump water heaters, and they will also support you with design guidelines and other information that's really helpful for a successful installation. They are currently working to compile all the parts and pieces, including the controls, the heaters, the storage volumes, and the electric resistance backup system when present, in a complete package so that it's a plug-and-play solution for the installing contractors. And so on the left-hand side, that's a sample schematic that we're helping them develop, and then we have a picture of 2 of these units plumbed in parallel. So this is a great option, which is on the table, and I would strongly encourage folks to go after it. The other point that I'd like to note is we've been talking about central heat pump water heating systems today, which is essentially providing a heater for more than one apartment. It doesn't mean that there's one central plant in the garage. You could have 2 central plants serving a 100-unit apartment building. One plant serves 50 in the east wing and one plant serves 50 in the west wing, or some scenario like that. It might be really advantageous with the Sandin or Sandco 2 products to put these on the roof because there's typically space up there with a small closet for storage tanks, maybe on the level below or on that roof level in a penthouse arrangement, and be able to have essentially zonal central systems. So maybe you have 2 to 3 systems, which each are comprised of 4 Sandco 2 heat pump water heaters and 1 200-gallon storage tank.
Colin, these things are about 3 feet tall. Is that about right?
Yeah, they're about the same size as one of those mini splits everyone's used to seeing. So maybe a foot in depth, 3 feet tall, and 2.5 feet wide.
And could you put them somewhere out in Eastern Washington where they get snow and all sorts of miserable weather and baking hot in the summer?
Yep. So these were located in Seattle during the great snowstorm of 2 years ago. And a tree branch actually broke off one of the nearby trees and hit one of these Sandco units right in the fan. But the other 3, there's only 2 shown here, but there's 4 total. The other 3 carried the building and through that period and met the hot water load. These devices do work down to about -25 degrees Fahrenheit and can provide full heat capacity down to about -5 degrees Fahrenheit. So I believe that's aligned with the climate conditions of Eastern Washington.
Cool.
Have a question for you guys. If you guys could opine on, if you guys could opine on a VRF system that has integrated water heating units, what is that implications on code, or could that be used? VRF systems that have integrated water heating units.
That's a great question. We've had success with some of those units in the past. They used a 410A refrigerant. So they have challenges making water much above 120 degrees. You can make water warmer than that, but then you're staging it or you have multiple compressors in series, which is not efficient. And they do provide, most manufacturers provide what's called a hydro kit, which is essentially a refrigerant to water heat exchanger. They also provide that with a compressor, which then it's essentially a heat pump, but it's a refrigerant source heat pump to potable water or to water. One of the challenges with those 410A equipment is they're originally designed for space conditioning where you don't have a potable water requirement. And in the United States, we need a double wall of separation between 410A and water that's used for drinking or bathing. And that you only need a single wall when it's used for space conditioning. Those devices have single wall heat exchangers designed into them. And so the designer specifying that system would then have to provide another heat exchanger and a pump to circulate through that system to provide your second wall. So it's a little bit of a more engineered system. What we've been focusing on today is technologies that you plug electricity into and they provide you with potable hot water for use in domestic applications.
Also note that such a system wouldn't qualify for that 5 credits as an advanced water heater because of the refrigerant it's using. So in Seattle anyway, it'd be a non-starter from that standpoint. Okay, we have to spend a little time talking about code requirements for work on existing buildings, and I'd like to start with these fundamentals. Okay, anything that went in when and met code at the time it went in can generally just stay there forever. You're almost always allowed to fix things that break, just putting them back the way that they were before. We don't do anything that will mess up historically important features of our landmark buildings. Those are irreplaceable, and we take that really seriously in Seattle. But on the other hand, new windows, new roofs, new lighting, certainly new water heating systems have to meet current code. And there are 3 categories of alteration projects that have to meet almost the whole new construction code. Substantial alterations, everybody's favorite thing if they're doing an alteration project, which is generally defined as a project that substantially extends the physical or economic life of the building. A change of occupancy from something funky like a factory or warehouse to something more polite like retail or yuppie condos. And any change of space conditioning, which means adding heating or cooling to a space that doesn't have it already. The idea is that these indicate a big project or a big repositioning in the market for a building. And this is not going to happen again for that building for another 40 years or something. So this is our most economical moment in the life of that building to bring it up to code. It's also one of those things that maintains my popularity ratings down in the low single digits all the time. And basically, if you replace, even without doing one of those 3 categories I just mentioned, if you just replace all or part of your service water heating system, the new stuff all has to meet code. We did make one big exception, and we've tightened up the language on that from last year, but if you need to replace just one boiler or one water heater in a crisis because it's failed or failing, we're not going to make you switch over to a heat pump water heater system because it just takes time to design and order and change out a typical gas system for a new heat pump system. But with that, Colin's going to talk about dealing with those challenges.
So this can be a challenge in both existing buildings and new construction, but a source to extract heat from, most commonly an air source. In multifamily buildings, I would highly encourage designers and installing contractors to utilize 134A equipment in an underground parking garage. You do need air source for those units, and that is a substantial amount of air. Here, we have 2 15-ton heat pumps and 1 7-ton heat pump. These are pulling about 20,000 CFM of air when they're all in operation together. And so we have some large ducting and louver requirements. You can get creative with these when they're inside of a garage. There's a site-proof louver shown on the bottom. That's, you know, what an architect ideally wants, but you could simply use a chain link fence or something like that that has more free area if you're dealing with a free area issue. But if you do have this on the side of your building, you do want some water prevention. Using kind of parking garage grates shown on the upper right there can be really helpful too. Those typically have pretty open free areas, and we can utilize more of a transfer duct situation where we're taking air from one level of a parking garage to another. And this can help extend our air path throughout the garage, or essentially put the heaters closer to the place where we want them, and just provide a transfer opening or ducted system to get air to them. But it is important to recognize that heat pumps do require an air source, both on to source air from, and you have to have a place to dump cool air to. Whereas your common gas water heater that you're familiar with, you might just have a 4-inch flue, and that's it. So more infrastructure here, but there's many ways to address the concerns.
And if that's a garage with a garage door on it, that can be a grill instead of a solid face door, and that can be a nice big opening for you.
We often see ventilated garage doors just for the garage exhaust system, and so that can be used in this purpose here too. We're used for this purpose. And the next challenge is just physical space, right? The heat pumps are bigger than a gas boiler or an electric resistance heater, and we're often providing more storage to get some of that cost benefit, trading off more storage for less heat capacity. So burying these in the garage, once again, is a great place, but you do have to work with the architecture to make sure that you have adequate space for these, and you're not confining yourself to a small closet that's unventilated, like an existing boiler room might be.
So, Colin, what building types or sizes would not be able to use arrays of those little stand-in units?
So we've served a 60-unit building with just 4 stand-in heat pump water heaters. And so that's pretty much the upper end of the extreme of that. You could serve a 100-unit building and combine a lot more of those together. That would work. But I would encourage designers to start thinking about how they can separate that single central system into 2 zonal central systems, because you will be significantly reducing your distribution losses, and that will mean you have to buy less equipment and your system will operate more efficiently.
Okay. One thing you should take into consideration with any alteration is this recent state law that impacts buildings bigger than 50,000 square feet in Washington. So for each occupancy type, they're establishing an EUI that buildings have to meet. And my thought is, for any building with a substantial water heating load, upgrading to heat pump system might be the least expensive way to take a building from below standard to above that line. And because it's just, as Colin mentioned at the very beginning, it's often happening in one space in the basement, and it's not that disruptive. And if at some point the city or the state adds carbon emissions to this building standards thing, this would also put your building in a much more advantageous position. The idea of burning stuff indoors to cook and heat water and keep warm has been with us for a long time. And that time is now over. Before this last decade or two, we really didn't have much in the way of options to replace these this fuel burning thing, but we can from now on think of buildings as a place that do not have to dump any kind of toxic stuff into the air we're breathing, and that are not going to explode periodically and are not going to cause those kind of problems. And at the same time, the fact that we can that getting away from burning stuff is causing us to be dramatically more efficient, it's a real win-win. So with that, I will close out here. Colin, did you have any last words you want to say to the people?
Just that I really appreciate your caveman technology slide.
All right.
No, I would just say that this has been done in high-rise construction, mid-rise construction, and low-rise construction. In multifamily buildings, it's common throughout Europe and other parts of the world. California is running full speed ahead with heat pump water heaters as gas is being phased out across most cities in California. So don't be afraid. It might be a little bit new to you, but there's support in the industry. The technology is available, and it's a great proven solution to save energy in multifamily buildings, as well as other building types.
Colin, we do have a few minutes. Do you want to show everybody that Eco-Sizer tool of yours? Could I just give you my screen?
Yeah, we haven't practiced, but let's try this.
All right. We'll see if it works.
Cannot take control.
Let's see.
Oh,
what about now, Colin?
Yeah,
awesome.
It's happening.
It's happening.
I don't know which screen it's going to show, so let's just. Okay. Can everyone see the Eco-Sizer now?
Yes.
Okay, awesome. So ecosizer.ecotope.com. You can make a bookmark for yourself. That will bring you to Sizer system page. There are some tabs up here. There's a glossary of terms and documentation, as well as our frequently asked questions and a little bit about the history of this tool. There's a brief explanation of the steps for success, but it's pretty straightforward. You'll notice that the first thing you're going to be asked to define are the number of people in the building. So we might have 150 people in our apartment building with 150 units. And if you hover over this question mark and click on it, you can bring up a further description of that, which is just pulling from the glossary section. So we define the number of people and the number of apartments we're serving. We're also going to define the peak gallons per person per day those occupants used. And so this is a simple slider, and we can leave it at the Ecotope market rate data with low flow fixtures, or you can bring it down to the ASHRAE low and all the way up to the ASHRAE medium. California, if you click on this California specification mode for those in that area or working in that area, it will default to the CEC's requirements for sizing of heat pump water heating systems. So going back, because we're in Washington State and Seattle, we're going to provide 25 gallons per person per day to 150 people and 100 apartments. Our design cold water temperature, we'll leave it 50 degrees. We're going to supply out to the building at 122. And we're going to store water in our primary storage at 145. There are some advanced options here, which I'm not going to go into, but I would encourage you to poke around. Here we have 3 configurations of our heat pump water heating system. We have the primary single pass heaters in series with a swing tank or the swing tank system. This is an electric resistance tank. So we overheat the water in the primary storage. As draws happen, that overheated water moves into the swing tank temperature maintenance tank and offsets any losses there. We also have a parallel system, which we're essentially providing a single pass heat pump water heater here and a multi-pass heat pump water heater coupled to a parallel tank. And then if you're in a small building or you have a heat trace system, you might have no recirculation system present. So I'm going to stick with a parallel loop tank setup for this project. There are some load shift capabilities, which I'm not going to go into now because they're a little bit more technical, but I would encourage you to explore those. So then you click the size your system button and you output to this results page, which you can save to a PDF and keep in your project folder. But essentially what we're coming out here is with a heat pump water heating system with our default selection point there in blue. Any system that's above this green line would meet the demand. So if we have, let's say we know we have a 120 kBTU CO2 heat pump available from Mitsubishi coming this summer. My default point is at 141 kBTU per hour. So I'm not going to meet it with just that one single heat pump water heater. So I'm going to drag my slider bar over and I'm going to go to, let's say, 120 kBTU or just under to account for some defrost factor. And so let's end up at maybe 115, 116 kBTU and 972 gallons. So in this situation, I might provide a 1,000-gallon storage tank or 2 500-gallon storage tanks to get my 1,000 gallons and 1 heat pump water heater to meet my primary heating load. The parallel tank volume, because I selected that, it will also give you outputs on this for how much heat capacity you need and how much storage volume you'll need there. And that is, there's an advanced option under there, and you can alter the cycling frequency and ratios to affect these two inputs, as well as your hot circulation losses. And so let's say if I were to slide this all the way to the left side of the screen, now we're going to have very little storage capacity at 313 gallons required. But we need now about twice as much heat capacity, 210 kBTU per hour. This is more reflective of your classic gas boiler system where we have very little storage and a lot of heat capacity here. So I would encourage you all to use this slider to find a system that works best for your project with both efficiency and economics in mind.
Okay, Colin, that's totally cool. And I think we're just right on time here. That is a really slick tool, I gotta say. So let's see if I can get back to sharing my screen. What happened here? Hello. Show my screen. All right.
Be able at this point. There we go.
Did it happen?
Yes, you are presenting, Duane.
I'm just trying to get to my screen, which is bound to be there.
As we set up here, Colin, do you mind? Someone's asking a question on, hey, is there a tool, or what we recommend for space type such as a school that has a high use for 3 lunch period than minimal?
That's a great question. I would highly recommend sizing your storage big enough that you have enough stored hot water to go through that high use period without running your equipment. And then your equipment can run for the rest of the period. You just want to make sure that you can recover before your next high use period happens. And the EcoSizer is currently only for multifamily building load profiles, but it's being developed to account for other load profiles, including office, hotel, education, and so forth.
Thanks a lot for that, Colin. Right now, we're going to actually launch a series of polls, and we're going to have a walkthrough with Julie Banerjee also on our panel here. And these polls, Julie, can you help explain what these polls are going to do for us?
Yeah, definitely. So I work in the part of City Light that's focused on programming and how to support y'all in the new construction space. So this will really help us understand the intentions that you have with your buildings in the coming year and how we can best support you to achieve your energy efficiency goals. So you can launch us, Armando, and we're going to start with some pretty simple questions about the code pathways that you're looking at. And so what path or strategy do you believe that you'll use more often in your next building? And we're talking about the C406 prescriptive path, the total building performance path, and the target building performance path.
All right, thank you for already starting to vote. We're getting a good amount of people voting in. And again, engage with us and we'll help our program developers understand how the industry is looking to meet that code compliance and then see how we can help with any programs along these lines. I'm gonna give it about 3 more seconds or 4 more seconds. I see some coming in still. All right, so good amount of prescriptive and total building performance. Not as much for that target building performance. Solid.
Great, thank you.
All right, now this one.
Yeah, as we're getting
As
we're getting more stringent with our code minimum efficiency, how likely will your future projects be above that minimum efficiency? Not at all likely, not really likely, neutral, somewhat likely, or very likely.
All right, and again, thank you for everyone that's jumping in and voting. Looking to see if we're going to be overachieving out here. All right, about 3 more seconds. We got at the very least, no one's a not at all. That is great. But good amount on the somewhat and very likely.
That's fantastic. That really helps us understand how to best help you. And since we're here today to talk about the water heating code requirements, what do you think are the barriers for your projects in meeting those water heating code requirements? And you can select multiple. So we have upfront costs, the technical knowledge or ability to meet the water heating code requirements, maybe supply chain issues, electric service connections. So when you're going in for that new City Light service connection, maybe the process or the associated costs, or actually the full life cycle costs. So both upfront and what you're estimating the operations, maintenance, etc.
Okay, about 2 more seconds and all right, pretty evenly spread. Actually, not really.
Yeah, we have some clear, upfront costs and that technical knowledge and ability. And that helps us, again, to understand how to best help you, particularly in new construction where projects, are so much. If incentives or if supporting the technical knowledge or ability is how City Light can support you.
Awesome. We're going on to our last poll.
Okay. Great. And so for those of you permitting through the C406 prescriptive path, how likely are you to propose the high performing service water heating for your options? So Duane went over those, whether it's proposed in your commercial buildings only, so that would be for the 5 points, proposing it in your multifamily, so those are R1, R2, for the 8 points. You know, if you're working on both commercial and multifamily buildings, proposing for both, or maybe you're going to use other credits, points or credits.
Okay, we're getting the answers in. Gonna be 3 more seconds. All right. Oh wow, good amount of people looking to propose for both.
Yeah, that's super interesting. And so thank you all for your responses. We're going to actually take the feedback from all of the trainings that we've had and incorporate that into our work. Feel free to reach out to myself for any questions about City Light's incentive programming.
I have a question that I see here that'd be good for us to opine live. It's more forward-looking. Does it appear that manufacturers of the water heater equipment will be able to keep up with increased demand from Seattle, Washington, and California? So is industry meeting code demand? Anyone care to opine on that?
I can take a start for it, and
Thank you, Colin.
that's that we've got a lag between when this code goes into effect, which is in a few weeks, and when that equipment is going to be getting installed in a new building. You think, you know, there's going to be a lot of people piling in just before the deadline, but say we start getting new applications under the new code, you know, in April or May. Those take several months to get their permit issued. It takes a year or so to get your hole in the ground and get a framework up. So somewhere around a year and a half, 2 years from now, we'll start needing to get that new equipment installed in buildings. And that gives everybody a lot of lead time and notice to start ramping up production of these, of whichever systems turn out to be the most popular equipment. Colin, do you have something on that?
No, I just generally agree with you, Duane, is like the staged implementation of this is something to be aware of. And also that there is equipment available now that you can purchase and has been available for the past 10, 15 years. We haven't seen any significant issues, but heat pump water heaters do have a little bit longer of a lead time than a gas boiler, which is what you're probably more used to.
Yeah, and actually, I'm glad Colin reminded me that the heat pump, the high performance water heating's requirements kick in for permits applied for starting this coming New Year's. So you actually even have more lead time, and this is exactly what that lead time was intended to help with, was ramping up manufacturing, engineering training, installer training.
All right. Well, thank you for the questions and for the participants. Thank you very much for engaging, for writing in the chat, for answering the polls. If you see on our screen, we'll have a recording of this session as well as a slide handout on our www.lightingdesignlab.org webpage on the education and resources tabs. You have Duane and my contact info on the screen, and I think we are right on time to close out shop. Thank you for those who've been here with us through all the 4 code update deliveries. It's been fun on this end. Hopefully it's been as much fun on the other end as well. So that is all, folks. Thank you very much, and stay tuned to further programming.